We have talked about doing inferences for one proportion. Now we're going to talk about doing inferences for two proportions and compare these two proportions by subtracting them. So here's the diagram that we've been working with this semester. Again, we have this population, and the numerical summary measure of that population, or parameter, is going to be denoted by pi1. So pi1 is the probability of success for population 1. Equivalently, you can think of it as, let's say, the population proportion for population number 1, or in some other applications, it might be, let's say, like a disease prevalence for population number 1. And we want to compare that pi1 to pi2, the proportion of successes, let's say, the probability of successes in population number 2. And the way that we're simply going to do the comparison is through subtraction. Now note that if this is equal to 0, notice what this says. This says that pi1 is equal to pi2. This is going to be of great interest to us. So again, similar to what we've done before, we take a representative sample from population 1. We also do it from population number 2. Now we have a more manageable set of information that we can work with. And so what we're going to do is calculate the statistics, the corresponding statistics for those two samples. So pi hat 1 is going to be the proportion of successes in sample number 1. Pi hat 2 is going to be the proportion of successes in sample number 2. Once again, you can think of it in different ways. For example, pi hat 1 could be, let's say, the observed prevalence from sample number 1. Pi hat 2 would be the observed prevalence for sample number 2, if maybe we're talking about estimating disease prevalences. So using this information from the samples, then we're going to try to make inferences back to those population values. So we're going to let y1 be the observed number of successes out of n1 trials, where n1 could be thought of as, let's say, the sample size that's coming from population number 1. Y2 is going to be the observed number of successes out of n2 trials from population number 2. And again, we're trying to estimate pi1, pi2, and we estimate it by the observed proportions. Okay, so similar to what we saw for dealing with one population proportion, we can find a walled confidence interval. Now here for the difference of these two population proportions, as we saw, or at least discuss, for one population proportion, this thing called the walled interval, or walled confidence interval, doesn't necessarily work as well as other confidence intervals. So we are not going to use this confidence interval in this class. But I do want to point out its structure. So we have the statistic. Here we're actually taking the difference of two different statistics, pi hat 1 minus pi hat 2. We have the quantile from a particular distribution. Well, it just so happens that pi hat 1 minus pi hat 2 has, for a large sample, approximately a normal distribution to it. So that's why we end up using a standard normal quantile. And then we take it times the square root of the variance of pi hat 1 minus pi hat 2. So we do that on the left side. Notice what's in the middle, pi 1 minus pi 2. And on the right side, we simply add that same set of quantities. Okay. So what we're going to use instead is what's called the Agresti and Kaplan confidence interval. The name Agresti should sound familiar because we use the Agresti-Kuhl interval when we were dealing with one proportion. So Alan Agresti is now a retired professor from the University of Florida's Department of Statistics. He's very well thought of in terms of being a statistician. For the Agresti and Kuhl interval, Kuhl was actually a student at the University of Florida and worked with Agresti to get that interval. Kaplan also was a student at the University of Florida about the same time, late 1990s, early 2000s, to do this corresponding work. And what Kaplan and Agresti said was, well, let's again use an adjusted estimator for pi 1 and pi 2. We're going to use pi tilde 1, pi tilde 2 as the names of those estimators or the symbols. And notice what we're going to do. We're going to add one success to the numerator, and then we're going to add one success and one failure essentially to the denominator. In other words, increase our sample size by 2. And we're going to do exactly the same thing for pi tilde 2. Note that this is very similar to what we did with the Agresti-Cool interval. The difference is that we always will have one success and one failure that we're adding for, let's say, sample 1 and also now for sample 2. Where before with the Agresti-Cool interval, our adjustment that we used was dependent upon the quantile from the standard normal distribution. Well, why are we using this different kind of adjustment here? Well, Agresti and CAFL did a lot of research into it for this particular interval, and they looked at other kinds of adjustments that one can make, maybe like add 2 successes instead, for example. And they saw that through their statistical research that this particular adjustment worked best. And so that's what we're going to do. So the 1 minus alpha times 100% confidence interval for pi 1 minus pi 2 is exactly the same as what we saw with the Wald interval, but instead of using pi hats, we're going to use pi tildes. And then we're going to adjust the overall sample size for the sample that comes from population 1 and also the sample that comes from population number 2. Otherwise, it's essentially the same as the Wald interval. Okay. So let me see here. I think I've talked about most of this. So just to emphasize, well, why am I saying this interval is better than using the Wald confidence interval? And this all comes back to understanding what a confidence interval means. And I've said this many times before, but this is sometimes a tough subject for students to understand, so I'm going to repeat myself here. So let's say that we go out and take samples from population 1 and population 2, calculate a 95% confidence interval. Go out and take another sample from population 1 and population 2, calculate the confidence interval. Let's say we do this 1,000 times. For a 95% confidence interval, we would expect 950 of these approximately to actually contain pi 1 minus pi 2, that true difference of the two, let's say, probability success parameters or proportion parameters. That's what we would expect to have happen. Now, with the Wald confidence interval, even if we say 95%, so we use alpha 0.05, the Wald interval very frequently is much less than 95%, maybe like 80% or 85%. Where the Agresti-CAFL won't always be exactly 95%, but it will be much closer than the Wald will be. And so that's why we use this particular interval rather than the Wald. Now, there are many other intervals out there for pi 1 minus pi 2. Just like with one proportion, there was many other intervals too. And to some respect, this is like a research problem that just never dies, because there's never going to be one interval that is always better than all the other intervals. But there is one other interval for pi 1 minus pi 2 that I would like to at least mention, although we won't actually go over it in class. And that is, there is an extension or the same idea behind the Wilson interval for just one proportion. Well, one can use that same idea to find a confidence interval for pi 1 minus pi 2. That particular interval works very well too, just like the Agresti and CAFL interval. Unfortunately, and a main reason why I'm not actually discussing here is that there's not a closed form expression for what that interval actually ends up being for all problems. So that means I cannot like write out one formula for it. Instead, numerical computation methods always need to be used to find this interval. If you're interested in actually exploring that on your own or actually implement it, my analysis of categorical data with R book does discuss this interval. Also, there is a nice function called diff score CI in R that will automatically calculate this interval for you. It is in a package called prop CIs. Okay, so let's take a look at an example. We're going to go back to an example we've discussed before. This deals with the Larry Bird data. So in the past, we basically analyze this data or examine this data as if this was the population of all possible free throws or pairs of free throws that Larry Bird could do. This actually isn't necessarily the best way to approach the problem, though. Rather, what would be better is what we're going to do here. So why do we do that before? It was to help teach basic probability concepts. So in this particular case, what we're going to do is consider that we have, let's say, two different populations. Population number one is with respect to made first free throws. Population number two is with respect to missed first free throws. So in other words, here is my corresponding population, my sample number two. This is my sample number one. And so Y1 is going to be 251. Y2 is going to be 48. I guess I should also mention. So what we're going to do is we're going to measure what is the probability of success or the proportion of successes for that second attempt. If you remember in our discussion in the past, that was a very important thing to examine, at least for basketball fans. Many fans will think, okay, if a particular basketball player misses that first free throw, so given that they've missed that first free throw, their probability of success will likely be less on that second free throw than if they would have made the first free throw to begin with. And the reason is because, perhaps when you miss that first free throw, maybe you kind of psych yourself out when you attempt the second free throw, and maybe you become down on yourself, and that might affect your ability to make that second free throw. So to some respect, what I'm doing is actually kind of stating a research hypothesis, and we will get back to that a little bit later. So that N1 is going to be 285, and N2 is going to be 53. Okay. So question, is this a representative sample? Well, this data actually came from two of Larry Bird's seasons. And, as long, I should say representative samples maybe. So as long as Larry Bird was consistent throughout his career, and he essentially was, except for at the very end when he was injured, this would be representative, even though it's even though it is not a random sample. But this is something to always think about with respect to sports data. Rarely can you ever actually get a random sample, and so you have to hope then the sample that you do get is representative. Of course, though, if it's not representative, then we got problems that any inferences that we make here could be incorrect. Okay. So we're going to let pi1, and we have to be a little bit careful about the wording because we have a first free throw attempt and a second free throw attempt. It's either made or miss, or you could say success or failure. We're going to let pi1 here be the probability of success, meaning you make it on that second attempt, for the cases where we have a first attempt that is made. We're going to let pi2 be the probability of success on the second attempt again, but now for the first attempt equal missed. Okay. So with that then, we can calculate now the corresponding estimated proportions, pi hat 1 and pi hat 2. So pi hat 1 is 0.88, pi hat 2 is 0.9057. Now here's a question for you. Suppose pi 1 minus pi 2 for Larry Bird here is equal to 0. What does this mean in terms of the problem? Well, let's think about it. What this is saying is that it doesn't matter what happens on that first attempt, because that second attempt for the population of all free throws, what happens on the second attempt is going to be the same in terms of the probability of success. And so also you should think about this, and hold on here, I might be foreshadowing some stuff coming up. Let me just Yeah, I'm going to delay the rest of that discussion for a little bit later. Let's go ahead and find the confidence interval then, using the Gressy-Caffel method. Sometimes it's hard to remember to say Kuhl or Caffel. Okay, so now with Larry Bird, pi tilde 1, our adjusted estimate, we add one success and we add one failure as well to our data. And so now our adjusted estimator is 0.878. Now look at that compared to what we would have had before when we just used the proportion of successes. And we can see that now this value is a little bit lower than what we had before. Pi tilde 2, 0.8909 now. Again, it's a little bit lower. And this corresponds to what we saw for the Gressy-Kuhl interval, where we're basically, this adjustment causes these estimated proportions or these estimated probabilities of success to be less extreme, meaning farther away from 1 or farther away from 0 than what the hat estimates actually end up giving you. And so then using that information, we plug in 0.878 for pi tilde 1, 0.8909 for pi tilde 2. We do that throughout, and we can't forget about that little adjustment to the sample size. And we get an interval of negative 0.1035 to 0.0778. Let's interpret it. I am 95% confident that the difference between the probability of success for the second free throw attempt is between these two numbers for successful versus unsuccessful first attempts, or made versus missed attempts. Again, another way to interpret this is that in all similarly constructed confidence intervals like this, we would expect 95% of them to contain the true values of pi 1 minus pi 2, or the true value of pi 1 minus pi 2. Well, let's take a look at how we can do this in R. So I'm simply going to enter in y1, n1, y2, n2. I'm going to do 95% interval, so alpha is 0.05. And we'll calculate pi hat 1 and pi hat 2, although we essentially don't use them for this particular interval. Now, while we won't use the walled interval, I did actually include the code to actually do the calculation if you wanted to see it. But what we're going to do is this Gressy-Caffel interval. So for pi dot tilde 1, y1 plus the adjustment of 1 divided by n1 plus the adjustment of 2. We do a similar thing for pi tilde 2. So let's just verify that indeed we did get what we want. And that's what we had before. Okay. Now, to find the lower bound, we take the difference of those two adjusted estimators, our quantile from our standard normal, and we take it times the square root of the estimated variance. How did I find that variance? Well, pi tilde 1 times 1 minus pi tilde 1 divided by n1 plus 2. I do the same thing with the second sample as well. So I use that then to find my lower bound. My upper bound is exactly the same, but now I put a plus there before the quantile from the standard normal. And then I summarize everything in a nice data frame. And here's our interval. Exactly what I had as when I wrote everything out. Okay. Well, let's look at another way to do some of these calculations here. There's a function called prop.test. In fact, we've seen that before. And in the x argument, what we can do is we can combine y1 and y2. So let me just show you that indeed we are combining into a vector y1 and y2. And then we add 1 to it. So let's go ahead, just let me show you what that looks like. And indeed, we're adding 1. Again, this takes advantage of how R nicely does its calculations. It would add 1 to both components of this vector. And then for the n component, we do this. We combine the n's. We add 2. We use conf.level equal 0.95. And then we also say correct equal false. The default is true. What this correct part does, it actually makes some adjustments, some further adjustments, which we don't want to have. I wish R wouldn't do it, but it is the default to do it. And so I want to say don't do it. And our interval is exactly as what we had before. There's some other information in the output that we will get to. As you might imagine, you could use prop.test to do a hypothesis test, but let me warn you that you should not use this particular output based upon this adjusted data to do the hypothesis test, because we actually don't want to use the adjustment when we use a test statistic or a p-value. And lastly, if you want to look at another method too, you can use the prop.ci's package I briefly mentioned before, and this wald2ci with adjust equal AC for aggressive CAFL will give you the correct answer. Okay, let me head back to the notes. Let's see here. So, question, is pi 1 minus pi 2 equal to 0? Well, again, our interval is negative 0.10 is less than pi 1 minus pi 2 is less than 0.0, about 8, if I round it. Is pi 1 minus pi 2 equal to 0? Well, 0 is in the interval, but notice other numbers are in that interval too. So, no, we cannot say it is. So this comes down to similar to what we do for a hypothesis test. We say, well, it might be, or there is not sufficient evidence to say it is or isn't essentially equal to 0. Now, this is an important question then. Are the first and second free throw attempts independent? And so let's actually go back in the notes from what we did before. When we were writing a contingency table out in terms of events and looking at probability structures like this, we said that if I condition on the row events and look at the probability that I get into that first column essentially, or the probability of B, and if these two probabilities are equal to one another, then I have independence. Because what this says, it doesn't matter if you're working with event A or A bar, the probability is exactly the same. That's independence. And in fact, that same idea is actually working here. Because basically what pi 1 is doing, it's like the probability of B given A, and pi 2 is like the probability of B given A bar. And in this particular situation, what we are finding is that pi 1 minus pi 2 could be equal to 0, meaning that pi 1 could be equal to pi 2. So in this particular case, again, we would say they might be independent, but we don't have sufficient evidence to say that if it is independent or dependent in this particular case. Okay. Well, what about hypothesis testing then? More formally, well, if we could use the confidence interval method, and do note that when I use this confidence interval method, I'm not guaranteed to get exactly always the same result as I will later on using a test statistic or p-value. Most of the vast majority of the time you will get the exact same result in terms of reject or don't reject, but there is a small chance you may not. So step 1 for a confidence interval method, we state our hypotheses. Step 2, we state our confidence interval. Step 3, well, because 0 is in the confidence interval, don't reject HO. And step 4, what does this mean in terms of the original problem? Well, there is not sufficient evidence to conclude that the outcome of the first free throw has an effect on the outcome of the second free throw. This corresponds to saying pi 1 is equal to pi 2. Well, maybe, but at least from this example, we cannot conclude that pi 1 does not equal pi 2. We can't, there's not sufficient evidence from this sample to make that conclusion. Okay, so that takes us to page 9. Well, what about now using a test statistic? Well, I guess, I'm sorry, let me back up here for a second. And perhaps I should have mentioned this before. You know, we can write out our hypotheses like this. Pi 1 minus pi 2 equals 0, which would be equivalent to independence. and pi1 minus pi2 is equivalent to dependence, meaning that those two probabilities are different, meaning that in the terms of the Larry Bird problem, it does matter if you make or if you miss that first free throw, because the probability of success is actually different on that second free throw. Now, this is a two-tail test. One could also look at a left tail or right tail test in addition, and we would have the same kinds of adjustments with respect to what the hypotheses would be. The actual, let's say, testing independence versus dependence doesn't necessarily work out as well, because now, you might have something like this, less than or equal to an HO and greater than an HA. And obviously, if you are less than, if pi1 is less than pi2, well, then you have a different kind of dependence. Okay, so the independence dependence only works with equal versus not equal. But again, you might want to do a left tail test sometimes. You might want to do a right tail test sometimes as well. You could also, in terms of the test statistic itself, if we think of pi hat 1 now as a random variable that varies from one sample to the next, pi hat 2 as a random variable that varies from one sample to the next, then and we make a similar statement as we've done many times before. Now, when we've done inferences, we know, or we can one can show that if I take pi hat 1 minus pi hat 2 as my random variable, subtract off a hypothesized value for the pi1 minus pi2, and then divide by the square root, what actually ends up being the variance of pi hat 1 minus pi hat 2. I get an approximate standard normal random variable. So what that means is I can make a probability statement that has a quantile from my standard normal on the left, quantile from my standard normal on the right, and say the probability of this all happening is approximately 1 minus alpha. Then what I can do is I can take this stuff that's in the middle here. I can then look at what will be the actual observed value. We'll call that little z. That can be my test statistic, but we're going to make one small adjustment to it. Because if I were to have, and we can just imagine, let's say this part right there was down there for now, rather than what I have written in terms of the p's. We would have a problem with calculating this test statistic because we don't know what pi1 or pi2 are. And we don't have really a good way necessarily, excuse me, we don't know what they are. But we do know that pi1 under the null hypothesis has to be equal to pi2. So how about we just call all this equal to pi sub p, for the lack of a better letter there. So what I'm going to do is write this what I had above in terms of pi sub p's now. Now the math becomes nice because we can factor out pi sub p times 1 minus pi sub p. And we're left with then here 1 over n1 plus 1 over n2. This is then what we use for our test statistic value. Well, how do you estimate though pi sub p? Because we still can't calculate it because this is an unknown parameter value. So the way that we estimate it is that, if what's happening in population 1 is what's also happening in population 2, essentially what that's saying is, well, we can combine the populations to come up with an estimate for the proportion of successes, or again, let's say maybe an overall disease prevalence. So we take y1 plus y2 all over n1 plus n2, and that's our estimate of pi hat sub p. And now this is what goes into our test statistic. Okay. So what are the critical values for a two-tail, left tail, and right tail test? And well, it all comes back to basically this expression here for a two-tail test. We're again saying, what would be reasonable values to observe for, let's say, a random variable z in this case? Well, you'd be between negative z sub alpha divided by 2 and z sub alpha divided by 2. Those would be the reasonable values. So we're going to use those for our critical values. Anything outside those two values, would be unusual if we had a small alpha, which we always do. So then on your own, you should think about, well, what will be the critical values for a one-tailed test? I'm sorry, a left-tailed test or a right-tailed test? And if you're not sure, you do need to ask. Well, what about a p-value? Again, remember what a p-value represents. Instead of looking at where you are on the x-axis of, let's say, a standard normal distribution, now we're looking at areas underneath the curve. And so the p-value for a two-tailed test would be 2 times the probability a random variable z is greater than the absolute value of the observed value for your test statistic. This is our measure of how extreme we are. On your own, again, you should think about what would it be for a left tail and also for a right tail test. So I've been talking about that we're using a normal distribution approximation here for the distribution of pi hat 1 minus pi hat 2 in terms of random variables. Well, when is this normal approximation, when does it work? Or when should we be scared that maybe it doesn't work? And there's a number of different recommendations out there. And here's my own. And that is, if you have any small cell counts, when you set stuff up in a contingency table like what we just got done doing, if you have any small counts, let's say less than 5, then you should start worrying if maybe that this normal distribution approximation will not work out well. And when that does happen, there are alternatives that one can use to check to see if the normal approximation works, or simply to do the inferences itself. We talk about those kinds of alternatives in my categorical data analysis course that I teach. So if you want to know more information about that, you can check out my course notes. I'd be happy to give you a particular reference. So let's, and I have a little bit more about that. I'm going to say a little bit more about that at the very end of our notes here. Okay, so let's go back to the Larry Bird example. We state our hypotheses. We find this overall estimate, or sometimes people call it a pooled estimate for the proportion, because we're pulling over the two different populations. And now we get 0.8846. So we plug that 0.8846 into the appropriate spots there. Notice we have a pi hat 1 and a pi hat 2 here. We don't have the pi tildes. We do the math, we get negative 0.52. For using alpha 0.05, our critical values would be plus or minus 1.96. And let's draw a picture. And so what we can see here is that this negative 0.52 is kind of in the middle of the distribution. It's reasonable, or you can say it's not unusual, to observe a test statistic around there. There's a lot of area underneath that curve there. So because of that, then, we can say, since negative 0.5222 is between our two critical values, don't reject HO. Again, just for emphasis, I always expect you to make a statement such as that. You always have to tell me why you don't reject HO. So what does this mean in terms of the original problem? Well, there is not sufficient evidence to conclude that these two probabilities of success are different. Or you can say to conclude that the outcome on the first free throw has an effect on the outcome on the second free throw. P-value method. Now for the p-value, we take 2 times the probability that random variable z is greater than the absolute value of negative 0.52. And essentially what we're doing is, if here's the absolute value, 0.52, we're calculating this area here. And since it's a two-tailed test, we multiply by 2 for that corresponding area, and we get 0.6015. How do I actually find that particular area? Well, I can come down to my p-norm function. Remember what this is going to be. Probability z is greater than, now positive 0.52. We can then use the complement and look at 1 minus probability z is less than 0.52. In R's terminology, this will be 1 minus P norm, Q equal 0.52. That's how you would do the probability part, and then you need to take this all times 2. Excuse me. So step 3, state your alpha value, 0.05. And step 4, well, because 0.6 is greater than 0.05, do not reject HO. Okay. In terms of doing some of these calculations in R, please take a look at this on your own. Again, it's just a matter of putting the mathematical expressions in terms of the R syntax. We've done very similar things like this in the past. Another way that we could perform the tests in R is use prop.test now. Now for our x argument, we use the unadjusted sample values. So y1, y2, n1, and n2. Conf.level is 0.95. Our alpha is 0.05. Correct equal false. And I just want to mention here too, even though this is the default, alternative equal 2.sided. We have a two-tailed test. There are similar alternative argument values that you can use for a left-tailed test and right-tailed tests. Okay, so here's our p-value that we've calculated before. This test statistic, let's call it x squared, 0.27. We saw this this issue back when we were doing this with one proportion, and what this actually is representing is the it's 0.52, what we got for z squared. And we talked about how a chi-square 1 distribution is the same as a standard normal distribution, essentially squared in terms of a random variable from a standard normal distribution. If you square it, that's equivalent to a random variable from a chi-square 1 distribution. The details of that are not important to us, other than you need to know why that test statistic there is labeled with an x squared, and also how that relates to what we actually have. And similar to also what we've done before, well, if we want to just get our actual test statistics itself, is z equal to 0.52 or negative 0.52? How do you know? Well, you go back to what pi hat 1 minus pi hat 2 represents. And in fact, R actually gives you pi hat 1 and pi hat 2. Notice when I do the subtraction, I get a negative value. So that means z is equal to the negative version, because z has pi hat 1 minus pi hat 2 in the numerator. Okay. So questions, are the first and second free throw attempts independent? Well, we don't know. There's not sufficient evidence to indicate that there's dependence. We at least can say that. Well, let's say, though, that this hypothesis testing problem was changed. You could say, I would generally say that for most basketball fans, their research hypothesis in this situation would be that the probability of success will be smaller on that second attempt if a basketball player misses rather than makes that first attempt. In other words, they would say pi 2 is less than pi 1, given how we constructed our contingency table. So what that means then is that our research hypothesis is pi 1 minus pi 2 is greater than 0. Excuse me. And so what we do is we, again, put our research hypothesis in HA. Because now if we reject HO, we are controlling the probability essentially of getting that wrong. Because our type 1 error rate is going to be, in our case, 5%. Okay, so let's say we did the test that way now. So this is a right-tailed test. Our test statistic, though, is negative 0.52. Our critical value, since it's a one-tailed test, a right-tailed test, is the positive critical value. And since it's a one-tailed test, then I do not take a divided by 2. I just have an alpha there. And so I get a positive 1.645. And here's a little diagram showing what's going on. Excuse me. And what we can see is that we're far from actually rejecting HO here. So we say because negative 0.522 is less than 1.645, do not reject HO. Again, there's not sufficient evidence to conclude that the probability of success on the second free throw decreases when the first free throw is missed rather than made. In fact, what we observed in the sample was the exact opposite of that. In terms of the p-value, now what we're trying to do is find the area underneath the curve rather than comparing values on the x-axis. That p-value ends up being 0.6992. If one were to actually do this in R, the quickest way is to use the prop.test function. Excuse me again. Where now for the alternative, we say greater, because we have the greater than sign in the alternative hypothesis. Here's the corresponding p-value. Okay. This takes us then to page 16. Now, sometimes when you do an experiment, let's say like this, or you get the data from someone else, the data will be structured in the following format relative to the Larry Bird data set here. Let's say the data is in a data frame called raw.data2, where each row of the data frame corresponds to each pair of attempts for Larry Bird, or in other words, each set of observations. So the first set of observations, he made the first, made the second. Excuse me. Same thing for observation 2, observation 3. Now observation 4 made the first, missed the second, and so on. And so maybe our data is constructed that way. Well, when that happens, you can go back to using that table function with it to actually find the contingency table. And so now I have all those cell counts, and I can proceed in the same way as I've done before. If you wanted to make it a little bit fancier, you put the results from table into an object called cont.table, for the lack of a better name. And then I can pull out what Y1 would be by the 1, 1 element. In other words, row 1, column 1. So the first number is always the row. The second number is always the column. We've seen this before with actual data frames. You can do a similar thing for Y2, N1, and N2 as well. Okay, now lastly, then, should we be concerned about the normal distribution approximation for this data that we're using? If you remember, I said if you have any cell counts that are maybe, let's say, less than 5, in other words, are small, excuse me, this is kind of a little bit of a warning bell. That's like, uh-oh, maybe this normal distribution approximation does not work. And so one thing that we would learn about in a categorical data analysis class, we talk about what are called exact inference methods, where we try to find the exact probability distribution rather than using an approximate probability distribution. We try to find the exact probability distribution for a statistic. And sometimes we actually have to use computer power to actually find what this distribution is. And what we have here, excuse me, is what's called a permutation distribution for these z's, without going into all the details. And by the way, I'm not going to ask you a question about this on a test or anything like that. And what this histogram is essentially an estimate of what the true exact distribution is for z. And we can see that generally speaking, it follows a pretty normal distribution, except for obviously we have some weird things going on right there. But otherwise, it looks pretty good. And there are other ways to examine as well. There are what are called quantile QQ plots or quantile plots, where we're looking for these points without going into all the details to fall in a straight line. The main thing I want to tell you is that the normal approximation does a pretty good job. It's definitely not perfect. And if you were to actually use one of these exact inference methods to find a p-value, guess what? The p-value is almost exactly the same as what we get. So that's why I'm not concerned about the normality assumption for the Larry Bird data. This concludes then this section or subsection on looking at inferences for pi1 minus pi2.